What happens? Is the camera going to stay on? So far, okay, keep our fingers crossed. So I welcome you folks. It's just about 2 o'clock on our Wednesday afternoon. I'll remind you about a couple of things. Number one, no lab next Monday, so a bit of a break. And in fact, we have one more wet lab, and that's lab H, so that's the following week, and then the lab exam. So we're getting quite close to the end of the lab component of the course. There's a weekly check-in that's due for this evening if you're doing that. And it seems that the Gradescope app for Android users, in other words, people using Samsung, I guess Google phone, the app seems to have developed a bug. I don't know how, whereas it appears to be working for iClicker. If you are an Android user, I ask you to please scan using a different scanner like Cam Scanner, and then uploading directly to the Gradescope website. If you're doing that, please use gradescope.ca. Log in to .ca, not .com, but .ca. Again, if you're having trouble submitting, please let me know. I can help. You can send me the PDF, although I prefer that you submit yourself. Right? So please let me know if you're having any challenges that way. And I guess I should mention that there's not a long interval between our last term test and the next term test. So the next term test is a week Tuesday, and the cutoff will be chem activity number 25. So it'll be once we've introduced Lewis structures. So we're going to start Lewis structures on Friday and mostly be done by the Tuesday, maybe a little bit into the Wednesday. So yes, go ahead.
So it won't be next Tuesday, it'll be the Tuesday after?
Oh, yeah, a week Tuesday. Yeah, no alarm there. A week Tuesday, because we still need to finish up to 25. Okay, chem activity 25. And this also reminds me to remind you that I am asking you to take a look at 2 video for chem activity 24 for Friday. And if you take a look at the remaining video that I'm asking you to take a look at, there's really only one more set, and that's related to chem activity 26. So if you say, oh, I'm tired of this assignment of video, well, we're almost done that as well. So those are my announcements. Please let me know if you have any questions about that. Okay, so I say we're taking a look at chem activity 23. I know you did the tutorial. Do be sure that you get to the last slide in each of the 3 different tutorials so that your grade gets submitted. If you did it and then you see that your grade isn't submitted, just let me know and I can adjust that. I trust you that if you did it, but you're not getting credit, that I want to make sure you get credit. Okay, but do check that you're getting credit for having done that tutorial. So I'm, in a sense, just going to do a quick overview of some of the highlights of that tutorial. And then I'd like to move on to the last little bit. So one of the things that I tried to establish in yesterday's class was that there are properties for these elements that are periodic. Just like any sort of periodicity, like the fact that we have lunar periodicity on the planet, the moon keeps coming around sort of thing. We have periodicity in the periodic table. And we like to try to use our understanding of the model of the atom to explain some of these properties. The only properties we are looking at is the size or the atomic radius, the ionization energy, electronegativity, and then we're going to look at ionic size. There are other properties that have been studied, for instance, reactivity or density. So those two can be related to periodicity. In general, the most important thing that's happening across the periodic table is that the charge is getting bigger in the nucleus. Now, I know that there are more and more electrons being added across the periodic table, but as it turns out, it's more important that the charge is increasing. And we see that because the atom gets smaller and smaller, even though there are more electrons that repel each other or one another, right? So as I say, the most important thing is the increase in nuclear charge. Down the periodic table, it's not that there are more protons and a greater charge, but what's more important is actually the size is getting bigger. So those two principles can guide you in making a lot of different predictions. So then, one of the things that I want to make sure that you can do is to actually be able to specify the trend. And I suppose you could try to memorize this. This is a chart on page 140, but I'm hoping actually you can kind of think it out. So if you haven't completed this chart, that is, sort of an overview of what the trends are, we should do that right now. So here, let me grab my pen. So I'm thinking, across the periodic table, I know that because the nuclear charge is increasing and the force of attraction between the nucleus and the valence electrons, which define the radius, is getting greater, that the radius is getting smaller. I know that it gets harder to remove the electron, which is related to the ionization energy. And the attraction for the nucleus and a shared pair of electrons goes up. Again, I wouldn't try to memorize this, but make sure that you know these trends based on the principles. Down the periodic table, the atomic radius is getting larger, because the valence electrons are further and further. It gets easier to remove an electron, less energy. And finally, the electronegativity goes down. So this chart summarizes these events. I will review each of them a little bit before we move on to the new things. Okay, so do make sure that you have that. And I suppose one of the things you could do before the next term test is, when you come into the term test, make a little sketch of the periodic table or use your periodic table and then just quickly put those out in case you want, you're afraid you might forget or get confused. So first of all, just a little quick review of atomic radius and also the way to be thinking about explanation. So I'm back on page 133. As you can see here, it's quite obvious what happens to the radius of an atom in relation to the main group elements. We often don't include the transition elements as their situation's a little more complex, involving electrons in the d orbitals, as you know. When you see this and you see the numbers, well, it's clear. Across the periodic table, the radius is getting smaller. Of course, you're not going to have that chart. You're just going to have the periodic table. The radius is getting larger down the periodic table. Again, you see it there, but you don't see it here. The whole idea of the radius, though, is kind of bizarre, though, actually, because when we draw this, it makes it seem like these atoms are billiard balls and there's a hard surface. Remember, the outer core, or pardon me, the outer edge of an atom is actually where we think the valence electrons are. But remember, we've been talking about valence electrons or electrons as waves. It's really tiny particles. So it's actually really amazing that these atoms behave like spheres, like there's a surface, but there isn't really, right? In some ways, it's hard to have a good analogy, but I think sometimes like a fan, see a fan whirling really quickly, it makes it look like there's this round object, where in fact there are just these blades. Right? But still, it's rather amazing, I find. Now, in terms of the explanation, you did some practice in the tutorial, and as you're preparing, I'd say, like, to give explanations, like for term tests, like if I asked, well, what's the trend across the periodic table, or compare these and explain why the radius is such, well, this is meant to help scaffold an argument. So the idea is that when we're talking about across the periodic table, we should always start with the wording, the nuclear charge. And as you know, the nuclear charge, pardon me, the nuclear charge increases across the periodic table. So that would be a statement. And then you could say, and therefore, the force of attraction between the valence electrons and the nucleus also increases. And then you add another sentence, and then you say, this results in the valence electrons being pulled closer to the nucleus, and therefore the atomic radius decreases. So that would be, I think, a nice little explanation for what's happening. Down the periodic table, the distance of the valence electrons increases. The valence electrons, therefore, are further from the nucleus. Therefore, the radius increases. So this was not just an exercise in making sure that you knew what the correct relationships are. It's meant to scaffold how to present an argument, if you will. Okay, so I won't say anything more about atomic radius. You've already done the tutorial. But I will ask you to do a little quick key question, which is, it's not a clicker question, but rather just a little exercise. It's found at the top of page 134. So based on what we were just talking about, will you kindly arrange these elements in decreasing size? So typically that would mean you would write the largest first, and then the next largest, all the way down to the smallest. So you want to order them in decreasing size, and see if you can do this without actually looking at those schematic balls that are on the front page. Can you do it just based on looking at the periodic table and knowing the trends? So I paused for a second for you to start to think about it. One of the things that I would think about doing is kind of orient myself and say, okay, what's the trend? What's the trend? Okay, across they get smaller, going down they get larger. Okay, so the biggest guys are down here. And the smallest guys are up here. And I would start at one end or the other. So I'm going to maybe start with the biggest. So, are there any elements in that list there that come from around here? Oh, yeah, there's barium. Okay, so barium is going to be the largest. And then kind of look, well, are there any that are up here? Oh, yeah, oxygen. So I'd expect oxygen to be the last. And, hopefully you've gotten started, but you might be doing something like, oh, and I also did this in case I didn't have my periodic table. So I've got a little small periodic table card here, which I got many, many years ago when I was a grad student at the University of Guelph, and I kept that. Anyways, you would start with, let's say, barium. And then you'd say, well, can I compare anything to barium? Well, I'm looking and I see scandium, I see gallium. So I know going up the periodic table, things get smaller. Okay, smaller. And going this way, they get smaller. So we would always give you something that you can actually compare, right? So there's not a conflicting trend. So I hope you would agree with me that the next one would be scandium, because going up, they get smaller. Going across, they get smaller. And I'm thinking, okay, I got to compare carbon, oxygen, or gallium. They get smaller, Oh yeah, of course, gallium would be smaller than scandium. So here I'm at gallium. Okay, I got to compare carbon and oxygen. Well, going up, things get smaller. So boron would be smaller than gallium, and carbon would be smaller than boron. Okay, so that kind of works. And then finally, oxygen. So there'll always be a way of comparing these. The other thing I would highly encourage you to do is put these greater than or less than signs, just in case you happen to put it in the opposite order. At least you'd be communicating to me that you know that oxygen is the smallest. So let's say you started with, let's say you missed the word decreasing size and you decided to list them increasing size. And if you do it legitimate, so you go oxygen, carbon, gallium standing in barium, and you show, greater than signs going this way, well then, yeah, I know you know what you're doing. Okay, so that's atomic radius. Questions about that? Good. Next. I'm going to skip ionization energy. I want to talk a little bit about ionization energy. So I'm going to skip right to electronegativity, just to make a couple of comments. So that was covered in the last of the 3 tutorials. And so this is found in your pages. Here, is it now? I should really staple this together. I see them. Okay. So it's found on page 136. Now, I don't usually just ask students for definitions, and like in terms of tests or whatever, but I think it's actually really helpful to know what the definition of electronegativity is. The attraction that the atom's nucleus has for a shared pair of electrons. So typically it relates to when we have covalent bonding, when we have shared electrons between atoms, and that's what we're going to be looking at on Friday. It was developed, the scale initially was developed by Linus Pauling. We're going to say more about Linus Pauling going forward. You can see that it's a unitless scale. So unlike radius, where you actually can talk about the size of the atom in picometers, there are no numbers here, or there are no units here. But we do see clearly that fluorine is the most electronegative, and rubidium, in terms of what we list here, is the least electronegative. Metals usually are not usually involved in covalent bonding. So there's sort of a bit of mental gymnastics to put, I think, those numbers together for metals. And we typically apply the electronegativity values more to elements that are involved in covalent bonding. So that would be these non-metals. I hope it's pretty obvious to you what the trend is, like increasing across the periodic table. So, and I guess I should also mention that because that word electronegativity can be tedious to write out all the time, we sometimes will just show its abbreviation. And technically, its abbreviation is this letter chi, which is also the abbreviation for mole fraction. But we do use it for electronegativity. I will be saying a whole lot more about electronegativity when we get to covalent bonding, so very shortly. So then in terms of trends, I would also like you to be able to predict the trend. So how about looking at this key question number 4, which is found on the next page. So that would be on page 135, I think. There we are. No, I lied. 137. Oh, I know. 137 is what I wanted to say. And I ask you to arrange these in increasing electronegativity. And if these elements look familiar, there's a reason. So it's found on top of page 137. Again, I would use the same sort of strategy, increasing electronegativity. So maybe I would look for those things that have the smallest electronegativity all the way to those that have the largest. And these are the same elements that we looked at just a minute ago. So once again, start with barium at the bottom, move to scandium, move to gallium, move to carbon, move to oxygen. And it would be something like that. And remembering that fluorine, oxygen, nitrogen, chlorine, those elements typically have the highest electronegativity. Again, why is that the case? Well, these elements experience the greatest nuclear charge across the periodic table. They're also among the smallest atoms, and therefore they really do experience that force of attraction of the nucleus. So I'm going to take a minute and just briefly talk about ionization energy. because there's a little special trend that happens there. So I'm going backwards now. So I'm back on page 134. I wanted to leave this to the last. We've met ionization energy before when we looked at the hydrogen atom and the energy that's required to take the electron from, well, it could be an excited state, but often ground state to infinity. It's the same principle here, right? But now we're looking at the first ionization energies for all of the elements. And instead of just saying ionization energy, we'd say the first ionization energy, because besides atoms other than hydrogen, they all have more than one electron. So we're talking about just to remove the first one. And I hope you see that there are some basic trends. Across the periodic table, ionization energy increases. So, hydrogen to helium, that's across the periodic table. Ionization energy increases. Lithium to neon increases. Sodium, argon, potassium, krypton, always an increase. But what I actually like for you to look at, like I like to ask about, are those strange dips that happen. Because I think it then shows you the power of looking at electron configurations and trying to say, well, can this explain actual observations? And note that those dips are not just anomalies. So you can see there's a dip between beryllium and boron, and magnesium and aluminum, and calcium and gallium. And there are dips between nitrogen and oxygen, phosphorus and sulfur, arsenic and selenium. We would expect dips between these guys. So I just want to briefly review one of the arguments related to the dips. And maybe as a fair warning, you'll see in past term tests, I ask about this and I like to ask about this. So just want to let you know. So one of the things that I tried to help you come to understand, and this is discussed in the tutorial, so it may even be worth going back through that tutorial. I'm just going to focus on the ionization energy across here. And the idea is that across the periodic table, of course, the nuclear charge is increasing. And if it was possible that all the electrons could have been jammed into the s orbitals, so it's not possible, just imagine for a minute we could. And across the periodic table, the nuclear charge gets greater and greater. Because the nuclear charge seems to override any repulsion of electrons, we would expect that the ionization energy would just keep getting bigger, bigger. Harder and harder to remove that electron. But you can see between beryllium and boron, there's a dip. But it's actually not quite right to just think the dip is happening here. The dip is actually happening for boron, carbon, and nitrogen, all of them, relative to what it would have been if all the electrons had been in the s orbital. But the idea is in going from beryllium to boron, you can now see we're removing electrons from the p orbital. So all of these are less energy than what you'd expect because they're from the p orbital. What's the difference? Why does that make a difference? The p orbital is further away from the nucleus. So all of them experience a little bit less tug of the nucleus. So yes, the nuclear charge goes up, but all of these electrons are a little bit further away from the nucleus. They're in that p orbital. So we usually ask you to explain between beryllium and boron. And that is discussed in the tutorial. But I would like to, in particular, look at this, nitrogen to oxygen. We get an even greater dip for these guys. And it's all for the same reason. And the reason has to do with, the reason has to do with, and we'll look at this in a second, I want you to focus here. So I'm talking in particular about, just to set the stage, I'm talking about why is there a dip from here to here, and correspondingly all of these. So one of the things that I often ask you to do related to that is, and this diagram at the top is found on page 136, and it's comparing nitrogen to oxygen. So please don't look at these just yet. Hold on, okay? Let's look up here. So let's look. We go from nitrogen to oxygen. The number of protons go up. We'd expect the nuclear charge to go up. We'd expect that these valence electrons would be more attracted to the nucleus. It'd be harder to remove them. And that's true if it doesn't matter which electron we're removing. Remember, all of these electrons in the p orbitals are degenerate. So, if we say, well, which electron is going to be removed if you're removing an electron from nitrogen? Well, it could be this, could be that. They're all the same. Whereas, if we look at oxygen, and I say, okay, which electron is going to be removed? What's the next electron? What's the electron that would correspond to the first ionization energy? They're not all equal. Which one would be removed?
On T1, is that
One of these guys? Maybe. Don't look at this just yet. So here, it wouldn't matter. Any one of them could be removed. So yeah, one of those could be removed, but what's going on here? We're allowed, and we've got 2 electrons in one little box. Now, how do electrons interact with each other? Is there an anomorous bonding or connection between them? They're both negative, right? So they repel.
Would it take less energy to take it out of the 2px because they repel each other?
Yeah, here, any one of these electrons could be removed. Okay? And compared to the element before nitrogen, which would be carbon, nitrogen's, requires more energy because with a higher nuclear charge, it could be any one of these. Okay? But now nitrogen to oxygen, yes, the nuclear charge goes up, but there's something else that changes. Now we're pairing up the electron, and therefore there's more repulsion. So I'm just seeing if any of that has made some sense. And the folks that went through the tutorial would have actually seen these questions, A, B, C, D. So I'm going to ask this as a clicker question now. So take a minute, and this is not in your course pack, so it might take a minute to read these. Just take a minute and read them. Which one of these statements expresses that idea that Nicholas was talking about? And the reason why I did different colors was so that hopefully it was easier to see the different lines. So which one of these describes that idea so that you could incorporate this in your explanation if you had to? And I'm looking here, and pretty awesome. Okay, so I see that folks are voting for A. They see that, and we say spin paired. So this be example of spin paired. Spin paired electron in the oxygen experience greater repulsion, and therefore it would be less energy to be removed than what you would expect, even though the nuclear charge is gone. None of these other statements are valid or correct. Like they all say require less energy, but The valence electron and oxygen atom is in a higher energy orbital. Well, no, it's still in the 2p. The valence electron's in a lower energy level. No, that's not true. The valence electron and the oxygen is all degenerate. Well, it's true they're degenerate, but the main reason is that, or the reason is we're starting to pair them. But note that for the next element, beyond oxygen is fluorine. And for fluorine, it would also be paired. And so for fluorine would be any one of these that would be removed. And you might say, well, why doesn't it dip more? Well, no, it's not going to dip more. It's just going to be continued to be dipped. So all of these are dipped from what you would have expected otherwise. We just happen to see the dip rate. So, it's one little case of, I think it's interesting that we can apply our understanding of the electron configuration to try to explain some pattern. You are, of course, welcome to go back to that tutorial if that would help you come to a better understanding or to review. Once you've done it once, the score is recorded. And so I'll stop for a second. Questions about that? Okay, so maybe some of you notice this picture, I don't know, right at the end of the third tutorial. This is Grant. Grant was sitting in seats where you are, well, not in this classroom, about a decade ago. So he was in Chem 112. And he went on to study biology. And then out of the blue, I get this email from him. And he says, Carl, are you doing any research over the summer? I said, well, no, I don't really do much research these days. But I do like to make stuff like activities and things. And I had already made the videos that you guys watch. And as you know, I have made a bunch of different H5P tutorials. So I said, but there's this. And he said, well, yeah, I kind of want to hone in on my chemistry skills for whatever reason. And so I showed him how to use H5P and I gave him the videos to work with. And so he put together, based on a template that I already had, essentially that tutorial. Okay, so former student, I have to admit, I went in and edited it a bit, but I think he did a very nice job. And so kudos to him. So at this stage, I think he was a grad student, I guess, a grad student studying marine biology. Okay. Yeah. And sometimes he has the beard, sometimes he doesn't. So let's move on then. Okay, this is the last part. We've got about a little less than 15 minutes, and that'll be good enough. So I'm looking on page 137. And the idea is here, I'd like to look at the last trend, like the last property that we're going to be looking at. And this will have parallels to what we've already done, but also take it to a different level. So we've already studied atomic radius, we've studied electronegativity, we've studied ionization. So now the last trend is ionic radius. But first of all, I'd like you to see what happens when an atom becomes an ion. And also to have a rough sense of why that might be. So just to pinpoint what's the change and how metals, when they become cations, and how non-metals, when they become anions, how those are different. So first of all, let's deal with the lithium atom, which is representative of essentially what happens with all metal atoms. So as you know, when lithium becomes an ion, its most stable charge is lithium plus 1. It loses 1 electron, loses 1 of its valence electron. I've tried to pinpoint or point out what changes in going from the lithium atom to the lithium ion. Number one, both of these particles still have the same nuclear charge. It's +3. They still have 3 protons. But you see that the size, and this is always true, I only pick lithium as an example, the size of the cation is always smaller than its corresponding atom. So what you see here is always true. It's smaller. Why is that? Well, we can't say It's because the valence electrons have a greater attraction for the nuclear charge. Sense? Because it's the same +3. Right? Other than these guys are shielded by those core electrons. So now that fact that is gone, these guys then, because there's one less energy level, will now see that entire +3. So the nuclear charge, in a sense, stayed the same. But because we have one less energy level, the valence electrons are actually going to see a bigger charge. So this will always occur when a metal atom becomes a cation. So cation is smaller because one less valence shell is occupied by electrons. The valence electrons are closer to the nucleus, and they would see more effectively that positive charge. It looks like I missed the word electron, so pardon me. Let me just put that in. So the nuclear charge in both cases is still +3. But because, when the valence electrons gets lost, now what were the core electrons, well, they have now become the valence electrons. So we have one less valence shell occupied. The valence electrons are closer to that nucleus. And in a sense, they will sense the positive charge of those core electrons, or those sense the positive charge of those core protons more effectively. So atoms that become cations, always smaller. What about the opposite? What about the fluorine atom becoming the ion? In this case, it's the same valence shell. All we're doing is popping in one extra electron. What always happens in going from the atom to the anion is larger. We can't say, again, that the nuclear charge per se changes, same number of protons. We can't say it's a different number of valence shells. We haven't lost a valence shell, if you will. So what did change? Why is this larger? Nicholas, what do you think?
There's like an intermolecular force between the electrons. Like adding another electron increases the repulsion.
Oh, okay, I like that. Okay, all right. We're going to reserve the word intermolecular force for talking about the forces between molecules, if you will. Okay, all right. Like London dispersion forces, dipole. But I like the idea that, yes, these electrons repel one another. So what you're getting a sense of is, if you keep the number of protons constant, but you add more electrons, it actually will affect the size. I want to contrast this. If we're going across the periodic table, the size gets smaller and smaller. So but you're adding more and more electrons. Yes, but you're also adding more and more protons. But if you keep the number of protons constant, yes, adding more electrons will also affect the size. And what does it do? It makes it larger because there's more repulsion. So you've got the key questions number 5. So 5, the cation is smaller because one less valence shell is occupied by electrons. Valence electrons are closer to the nucleus. And the anion is larger because there is more repulsion between the valence electrons. Yes.
A relatively smaller charge seen with electrons there, because relatively they sense smaller charge.
Okay. I actually don't, I don't think that's a great argument. Because in both cases, yes, you've got those core, well, pardon me. In both cases, you've got the core electrons that will shield to some degree the nucleus. So we could talk about an effective nuclear charge of, let's say, +7, and an effective nuclear charge, again, equal to +7. So both the electron, or the electrons in the 5 electrons that are in the p orbital, in the case of the fluorine atom, and the 6 electrons that are in the p orbitals of the anion, I think effectively they're both going to see a +7.
+7 divided by.
Ah, okay, all right. So okay, great. So what Samya is getting at is she's suggesting that, and I really like that suggestion. So you've got the 5 electrons pure, now you got 6, and with having an extra electron, make it harder for those electrons to see the nucleus, kind of thing, right? Okay. So how about this? So imagine that I'm the nucleus, right? And you guys are the one that's 2 electrons. Okay, so minus 2 electrons. And that row there, right, just along, and we got 1, 2, 3, 4, 5, 6. All right, so we just take 1, 2, 3, 4, 5. So we've got the 5 electrons there. Now we add the 6th electron. Adding the 6th electron, does that actually interfere with any of those guys seeing me? Right? So right, just by adding that extra one, like, so exclude Ben for a minute, right? Okay. So we've got those 5 electrons there. They can all see me to some degree. Yes, they're blocked by the front 2 here. Okay. But now we add Ben. So having those other 5, Ben, Ben can see me fine. Ben doesn't interfere with Jed seeing. Okay. But that said, they're all negatively charged. So they're spreading out. Okay, so really I think that the better argument is that what's changed in going from here to here is there's more repulsion. Okay? The argument in going from here to here, usually the focus is on the fact that there's one less energy level occupied. And therefore these electrons are naturally closer to the nucleus. And as I kind of alluded to, they're going to see that positive charge even better in a sense, because they're not shielded, right? But you can talk about that, but I think it's good enough just to say that there's one less valence shell, so they're closer to the nucleus. Are those making sense? No problem. So that's just going from the atom to the relative ions. But I'd also like us to be thinking about trends. So now that we've looked at this 5 and 6, let's turn the page and look at 138. Page 138. And I'll try to develop this argument as clearly as I can. Here I'm showing the more stable ions for the main group across the lithium to fluoride and sodium to chloride and potassium to gallium. But if I had more room, I could show them all. So these are now particles that are already ions. So we're not just looking from atom to ion, we're comparing ions, the more stable ions. Now, one of the points that I first of all want to make is you can't simply say, okay, across the periodic table, there's a general trend. Because you say, oh yeah, they get a bit smaller, but oh, now this is larger. So that's not going to work. And same here, they get smaller, but then those are larger. It's also not correct to simply say, well, anions are always bigger and cations are always smaller. what's true is the cation's always smaller compared to its atom. Anine's always larger compared to its atom. But I can't always say that an anion is larger than a cation. It depends. So, one of the things that we can say though, and a trend that's related to the atomic radius, is down the periodic table, it is true that the ions will get larger. So just like the the atoms, that's true. So you can see here, we can start with this, down a family. The distance of the valence electrons to the nucleus increases. The valence electrons are further from the nucleus. The ionic radius increases. So distance increases, further, the ionic radius increases. That's true. That's easy. So just like with the atom, down the periodic table, the ions get larger. But we need a different approach to explain what's going on, if you will, across the periodic table. So I say here in your notes, the only successful way to do this is to I shouldn't have covered that, is to consider the isoelectronic series. What do we mean by isoelectronic series? Atoms or ions with identical electron configuration. And usually this would be ones that are the electron configuration of the nearest noble gas. So to make this point, I am going to take this group, which I've highlighted in yellow, and I want to explicitly compare what's happening in a sense inside those ions in terms of the number of protons and nuclear charge and their electron configuration. But one of the things before we do that is just take a note. This actually is quite a nice trend. So this is the largest, smaller, 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 like that works, but let's see why we should be comparing them. So going down here, oh, I already did that. I have listed, and I started with oxide just so that the table wasn't too large, but I could have started with the nitride, left-hand side. And I've started, in a sense, to complete the table for us. There's oxide, fluoride, sodium ion, magnesium +2, aluminum +3. What about the electron configurations? Well, here's the electron configuration for oxide. 1s2, 2s2, and normally oxygen would be 2p4. But it's gained 2 electrons, become O2 negative. What would be the electron configuration for F-neg? Same thing, right? Write it in. It's the same as the nearest noble gas. We've seen this before. Here's the electron configuration for sodium +1. Sodium normally is 3s1. It's lost that valence electron. Oh, it's the same as the electron configuration as the nearest noble gas. So what about magnesium +2? Going to be the same. Be the same. So all of them are going to have identical electron configurations. They're going to have exactly the same number of electrons. This is what we mean by an isoelectronic series. So let's just grab that data that's in the diagram and plug those in. 140, 133, 102, 72, 54. Now, you don't memorize these numbers or anything, but notice the trend. The size of the particle gets smaller and smaller. And then let's see what happens to the nuclear charge. Now, what I mean by that is simply how many protons are present. So, of course, oxygen has 8 protons, fluorine 9, magnesium 12. So it's just the number of protons. So whenever we want to make a comparison of size, we don't just go right across the periodic table, but we start essentially here. And we compare these ions. But we don't stop there. We compare these ions to the cations that are here. We can go as far as aluminum. Because these ions up to here will all have the exact same electron configuration as the nearest noble gas, which is neon. That would be one isoelectronic series. Or we could start at phosphorus. Phosphorus, sulfur, chlorine would all have the same electron configuration as argon, and potassium, calcium, and gallium would all have the same electron configuration as argon. That would be another isoelectronic series. Now, why do we compare that series? Well, can you suggest a reason why the particles get smaller across an isoelectronic series? Is it because there's more electron repulsion or less electron repulsion? The electron repulsion would stay the same, right? Same number, exact same number of electrons. Size gets smaller. What does change? The number of protons. Right? So this is kind of like going across the periodic table, but in an even more dramatic way. Because normally for atoms across the periodic table, yes, the nuclear charge is increasing, but so are the number of electrons. Here, the nuclear charge is increasing and the number of electrons are staying constant. So there's going to be a really dramatic change in size. So the number of electrons stay the same, yet the nuclear charge increases. This is why the size of these gets smaller and smaller. Same with here then. All of these have the same electron configuration, same number of electrons, but the number of protons increase. Hopefully that chart kind of highlights. So look at the bottom then on the key question number 8. Across an isoelectronic series, the ionic radius, well, what does it do? It decreases. Why? Because for the exact same number of electrons, the nuclear charge increases. Therefore, there'd be more attraction of those electrons for the nucleus. So we've looked at a couple of different explanations here. So maybe just to kind of go back for a second, just because when you got a bunch of different things going on, it might be hard to keep it all together. So generally, across the periodic table, the most important thing is the nuclear charge is going up. Down the periodic table, the size is getting bigger. Comparing an atom to its cation, size always gets smaller. Why? Generally, we say it's because there's one less valence shell that's occupied. We lose those valence, so now the electrons are closer, right? So they're closer. They actually have a higher effective nuclear charge, but literally they're closer, right? These electrons here are in the first energy level. These guys are in the second energy level. So that's smaller. In this case, what's different? Well, it's not the nuclear charge that changes, but we added an extra electron. What's the effect of adding an extra electron? More repulsion. So bigger size. And then finally, we looked at this sort of thing. What happens in an isoelectronic series? And it's that same number of electrons, but the charge is going up. Now, what we often do here is we ask you to make a ranking. So let's see if we can do that. And this ranking is a little bit more challenging than the ranking just for atoms. So I'm looking on page 1 0.39 in conjunction, so with this chart. So I'm leaving this chart available. I'm leaving that chart available just to kind of help us guide a bit. Of course, you won't have that in the test. And I'm asking us to rank these guys. So this is the key question number 9 at the top of page 139. Rank the following ions in decreasing ionic size. So decreasing ionic size. So you want to start with the largest and go to the smallest. Now you can see I've listed things that are not, well, certainly not in this chart here. And in fact, there's one ion that's not even on this chart. Oh, where do we start? So I want decreasing size. Where should we look initially? And like, if you want to have a good chance of finding the largest particle period, where would be a good place to start? So further down, and like, it's not always true that anions are bigger than cations. It depends what you're comparing. But if you wanted, to maybe put things in favor of being the largest, would you look at an anion or would you look at a cation? I'm going to look at an anion, right? So I'm looking at all of these, and yeah, guaranteed it'll be the largest, but I'm going to compare this to this. Oh, well, how can I compare them? There's chloride. And going this way, things are getting larger. Can I compare somehow selenite to any of these? Where would selenite fit in this diagram? Where's selenite? Oh, it's right below sulfur. Oh, okay. So how about I add to my chart here? I'm going to put selenite. How would selenite compare? Would it be larger or smaller compared to sulfur? Going down the period, it's going to be larger, right? I don't need to know exactly what its size, but it'd be larger here, right? That's going to be bigger. So I think you'll find that's a good place to start. Selenite. And I think I crossed it out. So, okay, we've dealt with selenite. What can I compare against selenite? Well, I can compare sulfide. So I know sulfide would be smaller. Is there anything here that I can compare direct? Oh, chloride. Chloride would be smaller, right? Because that's part of an isoelectron series. So chloride would be the next thing that I can compare. All right, so chloride would be smaller. Now, here's where, like, yeah, students pretty good going across, but then how do I get to these cations? Well, I can't compare these anions to these cations directly. But I can compare these anions to these cations. These are smaller than these. They have to be. They're part of an isoelectronic series. So are there any of these cations in this list? Oh, yeah, right. Potassium, calcium, okay. Gallium. Oh, I can compare these guys all to chloride. They're all smaller. Okay, that's working out. So potassium, calcium +2, gallium +3. So I started with selenite. That was part of a different isoelectronic series. Selenite is part of the bromide, rubidium, strontium isoelectronic series. But then I got into the sulfide, chloride, potassium, calcium, gallium isoelectronic series. So that's, oh, what about aluminum? How does aluminum fit in all this? Well, aluminum's up here. It's just above. So what's the trend going upwards? It gets smaller. So yes, aluminum will be the smallest. So it'd be something like that. So again, you have to watch what you're comparing. questions about that trend? Okay, so I asked you to try one more then. So 9B asks you to compare yet a different trend. So here's 9B. See if you can rank those four. Similar approach. Even though anions aren't always the largest, depends what you're comparing, but that's a good place to start. So maybe start with the anion. So this is 9B. So I intentionally chose something that's not on the chart, like on our little diagram there, to see if you could see where it would fit in. So which would you expect to be the biggest particle? Yeah, iodide. So, I'm going to start with my anions, so between those two, right? Probably the iodide. So where's the iodide going to fit? Well, below chloride is bromide. So, I've got bromide in here. And below bromide is iodide. So iodide would be arguably the largest. And next, I can while I can't compare iodide directly to magnesium and beryllium +2, I can compare it to the chloride because chloride is found just above. Right? So going this way, things get smaller. Well, now that I've compared those two, can I compare chloride to anything else? Well, I can't compare the chloride to magnesium directly, but I can compare chloride to these guys. Coming along here, so chloride, potassium, calcium. I know that chloride is bigger than calcium, +2. And then going up this way, things get smaller. So chloride's bigger than calcium +2, which is bigger than magnesium +2. So sometimes when you're doing these, if it would help, you could always write in sort of an intermediate ion, if you will. So chloride would be bigger than calcium +2, which would be bigger than magnesium +2, which in turn would be bigger than beryllium +2. And there would always be a way of making the comparison. So again, the main issue is you need to compare along an isoelectronic series, and up and down, and I guess along an isoelectronic series, things get smaller, starting from the anion to cation, and then up and down, it always gets smaller going up. So to finish today, a couple of last check your understanding questions, and then we'll call it quits. Hopefully, after that little more difficult section, this is the check your understanding number 4. And I'm hoping this is actually pretty easy one, relatively speaking. So let me just open this up. So question number 4, and I'm just at group 1A, that's this guy, group 1, alkaline metals. Which schematic best represents what would happen? So assume that these are the atoms. Remember, group 1, they become ions, they're going to become cations. So what happens? What does that look like? I know that the scale's maybe not true, but what would be the best reflection of what happens when this atom becomes a cation? Both in terms of what happens in terms of the electron, but also to the size.
Only the size.
Pardon me? So you need to consider size as well, and you need to consider in terms of, well, what goes on with an electron? So I see some answers come in. I just want to sort of ask folks, so you got this atom plus an electron. That means gaining an electron. If something gains an electron, what charge does it become? Negative. Good, good. And then also, when an atom becomes a cation, what happens to the size? Always, even on Wednesdays. Right. All right. So fewer people are choosing that as an answer. Okay, good. And again, some people are choosing C. So it's true, right, that when something gains an electron, it becomes negatively charged. But do metal atoms gain electrons? Metal atoms don't gain electrons. Right. All right. So you've had time to vote in. Thank you. Unfortunately, I haven't quite helped people fully understand this, but at least half of you guys have chosen answer D, which is the correct answer. And the issue here is that when an atom becomes a cation, it loses electrons, it becomes positively charged, and the corresponding cation is always smaller. So in my mind, unfortunately, some folks chose E as the correct answer. So no, metal atoms do not become negatively charged. And some folks still insist on that. So no, those are not valid answers. So D is the best answer here. Well, what about the converse then, which is on the flip side? So this is on page 140. Which would best represent group 6A? So it's these guys. So what happens to them when they become ions? And this is representative of an atom becoming an anion. How do we show that? Okay, I'm pleased to see that the two favorite answers are ones that are showing electrons being gained. So that's good. So electrons are going to be gained. And when they're gained, there's more repulsion amongst the electrons, and therefore something happens. Okay, this is looking good. Better. All right, so most of you have voted in. It's been about a minute, so I'm going to close the poll. Okay, great. And by far, the majority of you have chosen the following, which is very nice. C. So electrons are gained. Therefore, the charge will be -2, and the anion is always larger than its corresponding atom. Let's do another quick comparison. So we got 2 more questions remaining, and then we'll call it quits today. So this is the, check your understanding, number 2 on page 139. So I'm going backwards a bit here. And one of the things that I said to you is you can't necessarily compare everything. But in this case, you see that what I'm comparing here is which of the following, I said atoms or ions. Clearly, they're all ions. Which one would have the smallest radius? And typically, actually, this is a fairly common kind of question on the test. So it's not like you got to compare absolutely everything. It's kind of sort of a localized set of comparisons. So you're looking for the smallest radius. And kind of think, all right, where should I be looking to find, should I be looking further down, or further up? So I see 2 favorite answers coming in. One of the things that might be handy is, so I'm going to write N3 negative. This is part of an isoelectronic series. And I know that N3 negative would be larger than O2 negative. And I know that phosphorus is below N3 negative, but phosphorus would be bigger, that's meant to be bigger than N3 negative. And then the other thing that I've got listed is sulfur. So I know that across the periodic table in terms of these ions, isoelectron series, that's smaller than that. I know that that's smaller than that. I can make those comparisons. And I can also compare these two, that that's smaller than this. So those are comparisons that I'm allowed to make. So here's one thing that I could not directly compare. I can't directly compare these two because they're conflicting trends. That's smaller than this, and this is smaller than that. So I don't know which is going to be a bigger effect. But the question was asking though, which one would overall have the smallest radius? And I see that indeed the majority of you have chosen answer A. And it would be the oxygen, right? So of all of these guys, this would be the smallest. N3 negative is smaller than P3 negative, and O2 negative is smaller than N3 negative. Right? So it has to be that the O2 negative is the small. And further, of course, we can do this comparison that we know that O2 negative has to be smaller than S2 negative. So overall, yes. And indeed, the majority of you have chosen that. So that's great. Finally, let's take one question a little bit away from looking at these ionic radii. This is the question number 1. So we're ending with the first question. And it says here, which of the following would have the lowest ionization energy? And let's see, do I have the diagram? No, I don't. But you have a little diagram there showing you the idea of ionization energy. So you've got like the nucleus, kind of a large nucleus, and you got this atom, and let's say the electron is in its energy level, and I want to remove it. And I'm comparing these 3 different scenarios. So just to be clear, the first one is helium ground state. The next one here is helium. I put a little star or asterisk. What's happened in going from A to B? Not just any heat. How's that different?
Looks like one of the ones got excited.
This is an excited state. Okay, so there's helium ground state, there's helium excited state, and then this is the helium atom. So I'm asking, which one of these would you expect to have the smallest ionization energy? Can you rationalize based on the things that we've been talking about? And so I'm just going to open this up. This will be the last. So it's not a typical, like, this is a first ionization energy question. It's seeing, can you read the situation? I will remind you that in all cases, given that helium atomic number 2, so we've got, two protons, we've got 2 protons, 2 protons. So in all cases, we've got 2 protons, so that stays the same. In all cases, we've got, well, no, maybe I should just leave it at that. In all cases, we got 2 protons. So if we had to remove the next electron, which one would be the easiest to remove? Okay, so most of you have voted in. It's been 1 minute. And so I think I've closed the poll. Look at that. Okay. Wow. By far, the majority of you have indeed selected this. And we're thinking, well, what would be the easiest to remove the next electron? If you're comparing these two, in both cases, you've got electrons in the 1s. In this case, in one orbital, you've got, and maybe if I just write it like this, you've got it in the 1s orbital, so you got 2 electrons, and here you got, and this will be the 1s orbital, and down here you've got the 1s orbital, you've got 1 electron. So why would it be easier to, or I haven't actually, we've been asking about this, but let's put it this way. Why would it be easier to remove that or one of these electrons compared to this? Given that, both of them have 2 protons. What's different between these two situations? Why would it be easier to remove these electrons?
Because that one has the assistance of the repulsion.
Yes, we've got the repulsion. It's easy to remove that. Between these two, that would be easier. This one, single electron experiences with 2 protons. So then that seems easy. Now, let's come here then. This is the easiest to remove. And it's 2 electrons. And this guy is already part way out of the atom. It's already in the 3 field. So this being an excited state has already had an energy input to get one of the electrons back. So in fact, it's already sort of taken advantage of that. So the electron is part way out. So the excited state atom is required to release things. So if I had to rank them, that would be the most, that would be the intermediate, and that would be the least. So the least ionization. Okay. Enough about trends in ionization energies. Friday, Lewis structures. Thank you for your kind attention.